a quick video about two sample proportional distributions where we're interested in the difference of proportions in two populations. This is very similar to the difference of means that we looked at in previous videos. So it's the same idea. We want to estimate the true difference of proportions, like how we'd estimate differences of means. So we're thinking like mu1 minus mu2, but we're talking about proportions instead of means, with the same ideas from one sample proportional distributions. And we're going to estimate that difference with two samples. One sample from the first population. We're thinking of that like the mean of the sample mean of the first population. And the second population. So we're thinking of it like x bar 1 minus x bar 2. So we take a sample to estimate the true parameter, the true difference. And here's our sample difference. And we can show that the standard error of this sampling distribution is a lot like the standard error of the one sample case, but you just add together a fraction for each of the samples. So here we have P1 times Q1. And remember, Q is just, that means 1 minus P1 in this case. That's our Q. And I should be accurate here. I'm going to put hats on these guys. Since our sample size is large, we can use our sample proportions in place of the true population proportions. So if we calculate that, we get our standard error. And this, of course, follows a normal distribution. And again, we just have to check that N1 and N2 are large. And by large, I mean the exact same thing I meant in the previous video. We need that N1 times P1 is greater than or equal to 15, and N1 times 1 minus P1, or times Q1, or we can use Q1 hat, is greater than or equal to 15. We're just checking against the proportion of successes in our sample and the proportion of failures in our sample. And it needs to hold for that second sample as well. N2 times P2 hat has to be greater than or equal to 15, and N2 times Q2 hat has to be greater than or equal to 15. So there's 4 different things you have to check here to make sure that this sampling distribution is indeed approximately normal. So let's do an example and we'll see how this works. Let's look at this example here. So let's say that there was an anti-drink driving campaign, or anti-drinking and driving campaign. In Europe they call it drink driving, but that's beside the point. An anti-drinking and driving campaign. They wish to ascertain if there's a difference in drinking and driving rates, which I'll call DD rates, before and after their campaign. And let's say the campaign ran for a year, just to say, a 1-year campaign. Doesn't really matter. Okay. Before the campaign, they sampled 500 drivers randomly, and they found that 8% of them have indicated that they have driven drunk at least once in the last year. Then they did it after the campaign with another, and this is a different 500 people. It's not the same. This is not a paired experiment. It's a different set of 500 people. 4% of them indicated that they have driven drunk. So, what we want, I'll write on the next slide. So what we're looking for is we want a 90% confidence interval for the true difference in proportion of drunk drivers before and after the campaign. And by drunk drivers, I mean those who have indicated they have driven drunk at least once in the last year. So the question that the campaigners asked the participants. Okay, so let's go ahead and do this. First of all, in order to do anything, we really have to make sure that our sample sizes are large. So remember that it was indicated that our proportion of success in our first sample, which I'll call PB for before, so that was 8% or 0.08, which means the proportion who didn't drink and drive, the failures, is 0.92. And we know our sample size, N before, is 500. And we know that the proportion after was 0.04. So the proportion of failures after was 0.96. And the sample size after was the same thing, 500. But remember, they were chosen independently. This only works if things are chosen independently. Otherwise, you have to look at some paired experiment or something similar to that. Okay, so let's test if N1 and N2 are both large. Okay, so let's go ahead and do this. Let's do N1 times, NB times PB. So how many of our 500 indicated that they drove drunk? And you can check that if I do multiply that, I get 40. And the other 360 did not drive drunk once in the last year. So they're both bigger than 15. We're good to go. Let's check the second sample. And after times P hat after. And you can check 500 times 0.04 is 20. That's getting a bit close, but for the purposes of this class, that's good enough. So we're still happy we can use the normal distribution to approximate the sampling distribution of differences. So that's good. And the number after times the probability of failure after. Remember, we're talking of success in this case as being a drunk driver. So it must be 380 that did not drive drunk. All four numbers are bigger than 15, so we're good to go. Let's sketch our sampling distribution. So the mean, or the true proportion, is going to be in the middle. So I have a hat there. I shouldn't have a hat. It should just be PB minus PA. And we want a 90% confidence interval. So the 90% is going to be in the middle. And on each side, because the normal distribution is symmetric, we have 5% of our data. And I really like sketching this diagram every time. I find it very helpful. And I suggest that you do the same thing. So we're looking for Z of 0.05. And if you look that up in your table, you should find that it's 1.6, we'll say 45. That's a little more accurate than, say, you'd get from the normal table. But if you used 1.64 or 1.65, either one of those would be fine for our purposes. Okay, so we need our standard error, and that's going to be the square root of P hat before, so that's 0.08 times 0.92, the probability of failure, over 500. That's our first sample, and we'll do it for a second sample too, 0.04 over 0.96, again, over 500. And we're going to take the square root of all of that. And so if you do that, you should get a standard error of 0.0, let's say 15. Let's round to the thousandths place there. Great. So, in fact, that's all we need is our Z alpha and our standard error. So, we estimate our 90% confidence interval is going to be our sample differences. So, the difference of before minus after. And if you did it the other way, after minus before, that's fine too. Plus minus our margin of error, or z alpha over 2. In this case, it's z 0.05 times our standard error. Remember, alpha is just the chance that we're outside of the middle. So that is 10% in total. So it's 5% on either side. So it's 10% divided by 2, 5%. And we put in our numbers, which just for the purposes of room, I will do on the next slide. So we get 0.08 minus 0.04 plus or minus our margin of error, so that our z alpha over 2 was 1.645 times our standard error, which we calculated to be 0.015. So this is going to be 0.04 plus or minus 0.02, let's say 47. And writing that in interval notation, that's 0.0153 and 0.0647. So we are 90% confident that the true difference in proportion of drinking and of drunk drivers before and after the campaign is 1.5% to 6.4% roughly, or 6.5% roughly, and that's before minus after. So that's 1.5% more before and 6.5% more before. So the true proportion difference is somewhere in there. Which means an important thing to note is that 0 is not in this interval. So we are 90% sure there is a difference, because we're 90% sure that the true proportion is within here. 0 is not within here, so we're 90% sure it's not 0. And that's very helpful to start to ask questions of, is some intervention actually helping a situation or actually making a statistical difference? And we use techniques like confidence intervals and something coming up later, hypothesis testing, to determine that. So that's a very key idea. But as you can see, building confidence intervals for these is basically the same as any other situation. You're just using a different standard error. And you just have to check that n is large enough that your sampling distribution will be approximately normal.